Okay, welcome again. So we have done the first property, the linearity property. It's a very important property of a system. We also have some other properties which have some relevance, and one among them is the invertibility. Although it's not that important a property, but still you need to know what what an invertible system is. So it's quite literal. Invertibility means that you have an inverse of a system. So to put it in a formal definition, a system is said to be invertible if the input of the system can be recovered from the system output. Fine. So it is something like this. You have a system. I'm showing graphically. You have a system. It has a system property h. You're applying a signal x of t, and it will do some transformation, which we normally show as y of t. Right? Now, when this transformation is done, and when I have the output y of t, if I want to derive my input back from this y of t, that is, so I need to do some inverse operation. Fine. So I need to have another system for which this y of t will act as the input, and it should give me what you call, it should give back x of t. Okay. For the time being, let's call it x prime, and let this system property be denoted by h inverse. Fine. Then x prime t, then okay, x prime t, it will be equivalent to this system property h inverse and the input I am applying to this second system. Okay. But we already know that y of t in itself is system property h acting on the original input signal x of t. So if I do this bit of manipulation, it will be h inverse h of x of t. Fine. So it will be h inverse h x of t. Now for x prime t to be equivalent to x of t, we have to ensure that h inverse into h should be unity. We say it should be an identity operator. Fine. Identity operator means it should be a unity value. Maybe आपने matrix में पढ़ा होगा identity matrix, something like that. Fine. Fine. So if this kind of a relation exists, I mean, if there is an operator h inverse which will act upon the output y of t and will give you back your original input, we say the system is invertible. So this is just a mathematical description. We will do a lot of analysis in this course. We will do one part of our analysis will be when we will be transferring from time domain to frequency domain. So there we use the concept of invertibility, because if you have a transform like Fourier transform which transfers from time domain to frequency domain, does the analysis in the frequency domain, then you should have an inverse Fourier transform that allows you to convert back from frequency domain to the time domain. So invertibility has an relevance in that sense also. Okay. Then the next property we have is based on the memory that a system may have. Again, it is a very straightforward property, and a system is said to have, let me write it down here, that a system is said to possess is said to have some memory if its output signal depends on past values of the input signal. Fine, because you need to store those past values, hence it should possess some memory. Fine. Like if I give a typical example, we did the moving average system somewhere like this one, moving average system. So it was average of the 3 recent samples. So if I take the same system, so if I have a system of the type y of n is equivalent to 1 upon 3 the current sample x of n plus x of n minus 1 plus x of n minus 2. This is the moving average system. Now evidently graphically, this is a system. You're only feeding x of n to get your y of n, but to get your y of n you also need previous 2 samples, which obviously means that you need to store these 2 samples. Hence we say this is a system which requires memory. Right? Now when the concept of memory comes, you also have to look into the to the extent. Okay, what is the amount of memory this possesses? Fine, it is basically the temporal extent of past values. Okay, how many past values you need to store, and in that way we express the memory of the system. For example, in this particular case, I need to store 2 previous samples. X of n is my current sample, it is available at the input. I need to store x of n minus 1 and I need to store x of n minus 2, which are the, so we say, sorry, so we say that the temporal extent of memory is 2 units because I need to store previous 2 values. Fine. Accordingly, your temporal extent of the memory, it may vary. So let me write it down here what I mean by this. So one important parameter with respect to this system is that the temporal extent, temporal means related to time, because n basically is is something which is related to time. In fact, it is a discrete value of time. So the temporal extent of past values means how many past values you have to store on which your output depends. This defines how far the, you can simply say this defines the memory requirement of the system. Fine. For example, in this moving average system, I needed, let me just first complete it. I needed 2 previous samples, n minus 1 and n minus 2. So the temporal extent was 2 units. So I needed a memory of 2 units for this moving average system. If you include more samples, for example, you have y of n is equal to, say I'm using a 5 sample memory system, so y of n is equivalent to x of n plus x of n minus 1 plus right up to x of n minus 4. Here the temporal extent is 4 units, which means you have to go 4 samples back in time, which need to be stored to get a faithful output from this memory average system. And so in that case, your memory requirement will be 4. Right? This is yet another property. Then we have one more property that is, again, it's a very important property. It's the property of causality. We will be discussing this a lot, using different methods, using different characterizations of the system. So again, it is a system. So let me write it down here, that a system, a causal system, is a one. So a system is said to be causal. A causal system is a one where the present value, if the present output value depends only on the present and or past values of the input signal. Fine. It has no dependency whatsoever on the future samples. Again, if I have to take an example, if we consider the same moving average system, so I have the moving average system y of n is equivalent to 1 upon 3 the current sample x of n and two previous samples xn minus 1 and xn minus 2. So as per the definition, it is only showing the current output, the present output. It depends only on the present input and the past values of the input. So this is very much a causal system. Right? So if I have a system, for example, if I modify the same memory average system like this, that 1 upon 3, I am taking a future sample xn plus 1, a current sample and a previous sample. Fine. Now it depends upon the current sample, it has dependency on the previous sample, but there also exists a future sample in the n plus 1 in the equation. So we say that this is a non-causal system. Right? Right here. So it depends upon what factors or what samples exist in your in your system equation. Right? Again, very important property. We'll be studying this a lot for different characterizations. Then yet another important property is the property of time invariance. Again, this is a very important property. And this actually shows the behavior of my system with respect to time. Right? First, we will have a formal definition that a system is said to be time invariant. So literally you can say which does not vary with time. If a time delay, sometimes since we are dealing things in mathematically, so we can also take into consideration time advance, although practically it is kind of complex that you will have, it's not that feasible that you will have a time advance. Fine, we will discuss that separately, but for the time being it's purely based from a mathematical point of view. So a system is said to be time invariant if a time delay or equivalently a time advance of the input signal leads to an identical time delay or time advance. So let me generalize it, leads to an identical time shift. Shift can be right or left, it may be delay, it may be advance in the output signal. Fine. So it means I have a system, it has some system property h, I'm feeding an input x of t and it is giving me output y of t. Right? Now for the same system, if I am delaying, if I am shifting my input, say from t to t minus t naught, where t naught is the amount of shift, and if I am getting an output wherein the shift is reserved, means it also has the same amount of shift, then I say the system is time invariant. In any case, if the shift is not preserved, means in your output you are not getting the same amount of the shift, we say it is time variant, that it varies with time. We will do some more analysis regarding the time invariance property. That will take some time, so I will have a separate video for that. That will be the next one. But this is the general definition and the description. So let me stop here.